GCE Advanced Level Chemistry Practical Series Experiment number 24, Observation of Reactions and Properties of Alkenes and Alkynes. To carry out this experiment, we have chosen ethene as the alkene and ethyne or acetylene as the alkyne. So we are going to subject ethene and ethyne into different chemical reactions, and we are going to observe how they react. So the aim of this experiment is to observe how the alkene ethene and the alkyne ethyne reacts with different chemical reagents and to observe their properties. Now let's move on to identifying the chemical reagents and the equipment we will be using for this experiment. Students, we have in front of us the chemicals and the equipment we will be using for this experiment. We have bromine water, potassium permanganate, ammoniacal silver nitrate or tolerance reagent. We have cuprous chloride, CuCl. We have ethanol, anhydrous aluminum oxide, also known as alumina. We have dilute ammonia, sodium hydroxide, sulfuric acid, and distilled water. Apart from that, we will be using cotton wool. We have a spatula, and we will be using a glass rod. We have some test tubes here. Please notice that we have labeled these test tubes. We will be taking different reagents that we have over here into each of these test tubes. To identify which reagent is present in which of these test tubes, we have labeled the test tubes. And then we will be using this retort stand, and on this clamp you can see we have a boiling tube fixed, and on top of this boiling tube we have a rubber stopper attached to a delivery tube. We will be using this setup to produce a gas, and the gas is going to be delivered with the help of a delivery tube into each of these test tubes. So we will be inserting the delivery tube and delivering the gas that is produced into each of these test tubes so that the chemicals that are contained in each of these test tubes can react with the gas that is produced. And we will be using a Bunsen burner as well. So these are the chemicals and the equipment we will be using for this experiment. Now let's move on to the first part of our experiment. Let's take a look at what we will be doing in the first part of this experiment. In the first part of this experiment, we are going to observe how ethene reacts with different reagents. So we have to first of all produce ethene. To produce ethene, we are going to be using this setup. We are going to take ethanol and react it with aluminium oxide or Al2O3, alumina. So when you are sending ethanol over heated alumina, ethanol undergo an elimination reaction to produce ethene gas. That is what this setup is for. So we will be producing ethene gas by sending ethanol or ethanol vapor over heated alumina. So when ethene gas is produced, the produced ethene gas is going to be delivered with the help of a delivery tube that we have over here, and we will be taking different reagents into each of these labeled test tubes. So to the test tube labeled A, we will be taking bromine water. To test tube labeled B, we will be taking alkaline cold dilute potassium permanganate. And to test tube C, we will be taking acidified potassium permanganate. And to test tube D, we will be taking ammoniacal silver nitrate. And to test tube E, we will be taking ammoniacal cuprous chloride. So students, let's take each of those reagents into each of those test tubes first, and then we can move on to producing ethene gas and making the ethene gas react with each of these reagents. So for the test tube labeled A, we are going to be taking bromine water. We have bromine water here. As you can see, we are going to take a small amount of bromine water into our test tube labeled A. As you can see, bromine water has a bit of a yellowish hue to it. As you know, bromine is red-brown in color, and bromine water is going to have this color that you observe here. Bromine water is used to identify the presence of unsaturated hydrocarbons. Unsaturated hydrocarbons are hydrocarbons that contain at least one double bond or a triple bond. And in the presence of a hydrocarbon that contains a double bond or a triple bond, bromine will attach across the double bond or the triple bond. Therefore, the bromine molecules that is found in bromine water will be used up, which will cause the color observed in bromine water to disappear. Bromine water will turn colorless if unsaturated hydrocarbon reacts with bromine water. So while keeping that in mind, you should observe that in test tube A, we have bromine water. Now let's move on to test tube B. Test tube B, we are going to include alkaline potassium permanganate. We are going to take dilute alkaline potassium permanganate. So we have potassium permanganate here. We are going to be forming a small sample of dilute alkaline potassium permanganate. To produce this dilute alkaline potassium permanganate, we are going to take a small amount of potassium permanganate into a boiling tube, like so. And then we are going to add a base to it. We can add sodium hydroxide that we have here. And by adding sodium hydroxide, we will convert this aqueous potassium permanganate into alkaline potassium permanganate. We have added a small volume of sodium hydroxide, and now what we have formed here is alkaline dilute potassium permanganate. We know that the potassium permanganate solution is a dilute solution because if you have conducted experiments with potassium permanganate, if you take concentrated potassium permanganate, it is going to have a very dark purple color. It's going to be a very deep purple color or a very dark purple color, which is going to be somewhat different to the color that a light purple color that you observe here. So what we have here is a dilute alkaline potassium permanganate solution. So let's take a small amount of this cold dilute and alkaline potassium permanganate solution into a test tube. And this test tube that we have here is labeled B. So in the test tube that is labeled B, we have our dilute alkaline potassium permanganate solution. Now we will be moving on to our test tube C. Now, as I mentioned earlier, test tube C should contain acidified potassium permanganate. So let's prepare a small sample of acidified potassium permanganate. Let's take another boiling tube and take a small volume of our dilute potassium permanganate solution here. And to this potassium permanganate solution, we are going to add sulfuric acid. The addition of sulfuric acid is going to make this potassium permanganate aqueous solution into an acidified potassium permanganate solution. So let's add a small volume of sulfuric acid. Now, after the addition of sulfuric acid into our potassium permanganate solution, we have prepared acidified potassium permanganate solution here. Let's take a small amount of this acidified potassium permanganate into our test tube labeled C. Now we can keep this boiling tube away. Afterwards, we have to move on to our test tube D, which should contain ammoniacal silver nitrate. In other words, tolerance reagent. We have a prepared tolerance reagent here. So we can take our tolerance reagent and add a small volume of our tolerance reagent into our test tube here. We have taken ammoniacal silver nitrate or tolerance reagent into this test tube. You can see it appears clear here, and what you have here in this test tube or test tube D is ammoniacal silver nitrate, or in other words, tolerance reagent. Now students, let's move on to our test tube E. Now the test tube E should contain ammoniacal cuprous chloride. We have cuprous chloride here, we have distilled water and ammonia. So we can now move on to produce ammoniacal cuprous chloride. So first we have to take our cuprous chloride solid here. If you take the cuprous chloride solid, if you take a spatula and introduce a small amount of cuprous chloride, a very small amount of cuprous chloride into this boiling tube, and then we can move on to add a little bit of water to this. We have distilled water here. Let's add distilled water to dissolve this cuprous chloride we have here. Now students, the cuprous chloride solid is a green color solid. Cuprous chloride is a green color solid, and when we dissolve it in water, the solution that is produced is also going to be green in color. We have cuprous chloride. Some of the cuprous chloride is not dissolved here in this particular solution, but when we add ammonia, we are going to see most of this cuprous chloride will dissolve to form a complex with ammonia, and the solution will change its color from this green color to a blue color. So let's take a small amount of dilute ammonia. We have our dilute ammonia bottle here. And let's add a small volume of dilute ammonia into this boiling tube. You can see when we add dilute ammonia, the color is starting to change into a blue color. We'll add a bit more ammonia. And let's mix it all really well. Now students, we have dissolved all the cuprous chloride and formed ammoniacal cuprous chloride here. We initially dissolved the cuprous chloride in water. We saw some of the cuprous chloride solid didn't dissolve entirely in water, but after the addition of ammonia, all of it dissolved to produce our ammoniacal cuprous chloride that we have over here. So what we have here is our ammoniacal cuprous chloride. So let's take this ammoniacal cuprous chloride solution into our test tube E. We have in our test tube E ammoniacal cuprous chloride. So before we start producing ethene, let's go over what we have in each of these labeled test tubes. In test tube labeled A, we have bromine water, which is yellow in color. And then we have in test tube B, dilute alkaline potassium permanganate. In our test tube C, we have acidified potassium permanganate. In our test tube D, we have ammoniacal silver nitrate, or in other words, tolerance reagent. And in the test tube E, we have ammoniacal cuprous chloride. Now, let's move on to producing ethene gas. Now, we are going to be moving on to producing our ethene gas. So students, to produce the ethene gas, we will be needing a boiling tube. We have a boiling tube here, and to this boiling tube, we are going to add ethanol up to about a height of 2 centimeters, and then we are going to introduce some cotton wool to soak up all the ethanol that we have introduced here. We are going to then slant this boiling tube and introduce some alumina to the middle part of this boiling tube. So the reason for us to introduce our cotton wool is to make sure that the ethanol doesn't flow over the alumina that we have here. Cotton wool will absorb the ethanol, and when we turn this boiling tube horizontal like this, ethanol will not flow towards our alumina that we have in the middle of the boiling tube. That is the reason for us to add our cotton wool. So now let's take our ethanol that we have here, and we can add a small amount of ethanol. We can add a small amount of ethanol into our boiling tube. We have added ethanol into this boiling tube, and the ethanol level is about 2 centimeters from the bottom of our boiling tube. So after adding ethanol into the boiling tube, the next step would require us to add some cotton wool. So you can take about 2 pieces of cotton wool, and we can push it towards the bottom of the boiling tube with the help of a glass rod. Now students, when we turn the boiling tube, do you see any ethanol flowing towards the middle bit of our boiling tube? You do not. The reason for this is ethanol is soaked into or absorbed into the cotton wool. So therefore, it will not allow the ethanol to flow and fall out, or if you turn it upside down, you do not see the ethanol falling back out of the opening of the boiling tube. Right, so when you turn it upside down, you will not see any ethanol flowing out. This is because we have inserted a cotton wool and the cotton wool has soaked up all of the ethanol. Now, let's move on to adding some alumina. So as you saw students, the ethanol did not fall out of the boiling tube when we placed the boiling tube horizontally or when we inverted it, because the ethanol is absorbed or soaked into our cotton wool. So now let's move our ethanol and let's take our alumina or aluminium oxide, and we have to take a small amount of alumina and place it on the boiling tube here. We have to make sure the alumina is present in the middle of the boiling tube, somewhat close to the cotton wool. So first of all, let's place this boiling tube in the setup that we have here. After placing our boiling tube here, we can move on to taking a small amount of alumina right. Alumina is a white color solid. This is anhydrous aluminium oxide. We can place a small sample of alumina in the middle of our boiling tube like so. Now students, after adding the alumina, we can move on to close up the boiling tube with the help of a rubber stopper. We have our rubber stopper here. We can close it up with the help of this rubber stopper, and this rubber stopper is connected to a delivery tube. So this delivery tube will help us deliver the gas that is produced into each of these test tubes. So we have our test tube labeled A to E here, and you know what compounds are there in these test tubes. And we are now going to start our reaction by heating the alumina that we have here. And as we provide heat, as you know, ethanol is a bit of a volatile organic compound. So the ethanol that we have soaked up into the cotton wool will evaporate, absorbing the heat, and will go over the heated alumina. This will produce ethene gas. As you know, when we have alumina or aluminium oxide as a catalyst, and when you send ethanol over heated alumina, an elimination reaction takes place where ethanol gets converted into ethene gas, releasing water. So the ethene gas that is produced is going to be introduced into each of these test tubes with the help of our delivery tube. So students, since we know what is happening here, let's move on to actually conducting this experiment. And as I introduce ethene gas into each of these test tubes, you have to observe the color change that takes place. So let's turn on the Bunsen flame or Bunsen burner here, and then conduct our experiment and produce ethene gas. Now, Let's light our Bunsen burner and start our reaction. So we'll light our Bunsen burner and we can start heating up the alumina that we have here. We can lower the entire setup like this, and as we heat our alumina, we can insert this delivery tube into our bromine water. And as you can see, there's a gas that is being produced, and the gas that is produced is it decolorizing the bromine water? Do you observe the color of bromine water changing? The answer would be yes. The color of the bromine water is gradually decreasing. As ethene gas comes into contact with bromine water, ethene will react with the bromine in this bromine water, and as bromine gets reacted, as bromine gets removed from this aqueous medium, the yellow color or yellow-brown color that you observe here will disappear. This yellow color in bromine water is there due to the presence of bromine water, and as we can see, there is still a small yellow color that we can observe here, but as the reaction proceeds, as more and more gas reacts with this bromine water, the color of the bromine water will completely disappear and we will observe the formation of a clear solution. This is because the ethene gas that is produced here is going to react with the bromine present in bromine water and will turn bromine water colorless. So this is now almost entirely colorless. You can see here, initially when we were starting off, bromine water was not this color. Bromine water had a yellow hue to it. Usually bromine is red-brown in color. Bromine water will have a brown or yellow color to it, and you can see the yellow bromine solution that we took, or bromine water that we took, is now colorless after sending ethene gas through our bromine water. This indicates that the gas that we produced was in fact an unsaturated hydrocarbon. Let's try and react this ethene gas with our contents in test tube B, which is alkaline potassium permanganate solution. You can see, as soon as we introduce this gas, first of all the color, purple color, turned into a green color, and now if you continuously send this gas, you will observe that this green color turns into a brown precipitate. Since the precipitate is going to be suspended in the aqueous medium, it will appear like a brown suspension or brown solution, but you have to keep in mind it is not a solution, it is a suspension that is going to be formed. First thing that we observed was the purple color potassium permanganate alkaline solution turned into a green color. This is due to formation of potassium manganate or manganate ions. Manganate ions are green in color, but now you can see this green color is gradually changing to form a brown color suspension. Do you see the green color disappearing little by little? The green color is disappearing to form a brown color. This is because of the formation of MnO2, manganese dioxide. Manganese dioxide is a water insoluble precipitate. This water insoluble precipitate that we have here is going to be suspended in the water as fine particles, and you will observe it like a brown color suspension or brown color aqueous solution. But you have to keep in mind, it is not a brown color aqueous solution. It's in fact a brown color suspension. Right, students? So now we have gotten through that point. You can observe that we have formed our brown color suspension. We started off with a purple color solution. Alkaline potassium permanganate was a purple color solution. Then later on, when we introduced ethene, what happened? It turned this potassium permanganate into potassium manganate, which was a green color solution, and then to this brown color suspension, which is due to the formation of MnO2 or manganese dioxide. Now we are going to introduce this gas that is formed into acidified potassium permanganate. When we introduce it to acidified potassium permanganate, you can see the color of acidified potassium permanganate disappearing very clearly. You can see that here. Very clearly, very gradually, the color of the potassium permanganate completely disappeared. The color of the potassium permanganate can no longer be observed here. So when we use acidified potassium permanganate, the observation is the color of the acidified potassium permanganate, purple color, completely turns colorless. This is due to potassium permanganate or permanganate ions turning into Mn2+. In test tube D, we have ammoniacal silver nitrate. Now we are going to be sending we are going to react ammoniacal silver nitrate with ethene gas that is produced here. We will not observe any reaction when we send ethene gas through ammoniacal silver nitrate. Ammoniacal silver nitrate or silver plus ions do not show a reaction with ethene gas. However, we can't say the same for ethyne gas. We will observe that in the next part of this experiment. What about ammoniacal cuprous chloride? We'll send ethene gas through ammoniacal cuprous chloride. As you can see, when we send ethene gas through ammoniacal cuprous chloride, we do not observe any further reaction. The color of the cuprous chloride did not change. Now students, we have conducted the first part of our experiment. Let's take a look at what actually took place in each of these reactions. In our test tube A, we had bromine water. To observe the initial color of bromine water, we'll take another test tube and let's take a small sample of bromine water into that test tube. Now students, you can see the initial color of bromine water was yellow or yellow brown in color. However, after we sent ethene gas through the bromine water, we can see that the bromine water has gotten decolorized. Why did the bromine water get decolorized, students? When bromine comes into contact with ethene gas, due to the double bond that is present in ethene gas, bromine molecules will get added onto the ethene molecule to produce 1,2 dibromoethane. So when it comes to any unsaturated hydrocarbon, if you react it with bromine water, the bromine molecules in the bromine water will get added to that unsaturated hydrocarbon across each double bond, and when this reaction is taking place, the bromine in bromine water will get used up. So therefore, the color that is observed in bromine water, this color that we observe here in bromine water, is due to the presence of bromine molecules in bromine water. As bromine gets used up, the color disappears. As you can see in test tube A, when bromine water reacted with ethene gas, the color disappeared and we have a clear solution formed in test tube A. So we understood through this experiment that ethene gas will react with bromine water and will decolorize bromine water. In fact, we use the bromine water test to identify hydrocarbons that are unsaturated. It is a test to identify hydrocarbons that has an unsaturation in them, or that has a double bond or a triple bond in the hydrocarbon, can be identified with the use of bromine water. Then we took to test tube B, we had alkaline dilute potassium permanganate, and the alkaline dilute potassium permanganate was purple in color. Alkaline dilute potassium permanganate was purple in color, but when we reacted this alkaline dilute potassium permanganate solution with ethene gas, the alkaline potassium permanganate was able to oxidize the ethene gas and produce diols or a glycol. So across the double bond, two OH groups were attached, and this causes the ethene gas to get oxidized, and as the ethene gas got oxidized with the help of potassium permanganate got reduced. Starting from permanganate ions that are purple in color, we observe the color of this test tube changing from purple to green first. That is due to the formation of manganate ions, MnO4 2 minus ions, which is manganate ions that are green in color. Afterwards, these manganate ions further got reduced to form manganese dioxide, which is a water insoluble brown color precipitate. And what you can see over here is the suspension of MnO2 brown color precipitate. The fine particles of manganese dioxide is spread throughout this aqueous medium, producing this brown color suspension. So ethene gas reacts with alkaline potassium permanganate and convert the purple color alkaline potassium permanganate first to a green color, forming manganate ions, which are green in color, and then they further get reduced, manganate ions further get reduced to form manganese dioxide. And while this is happening, ethene gas got oxidized to forming diols, or also known as glycols. So when you are reacting ethene gas with acidified potassium permanganate, we saw the acidified potassium permanganate is purple in color. The purple color of the acidified potassium permanganate completely disappeared when we reacted this acidified potassium permanganate with ethene gas. Just like in the previous instance, ethene gas, when reacted with potassium permanganate, got oxidized to form diols. Across the double bond, two OH groups got attached to form a diol, and while the ethene gas got oxidized, the potassium permanganate that was present in acidic medium got reduced. In acidic medium, the permanganate ion can get reduced all the way to Mn2+. So Mn2+ ions are colorless. Although Mn2 plus ions in aqueous medium are said to be slightly pink in color, this very low intensity pink color is very difficult to observe in lab environments. So we are going to observe the formation of a colorless solution instead. We are going to observe the formation of a colorless solution instead. So what you have here is Mn2 plus ion solution that was formed due to reduction of permanganate ions into Mn2 plus. Now students, in acidic medium, permanganate ions get reduced all the way to Mn2 plus. In alkaline medium, permanganate ions can only get reduced up to MnO2 or +4 oxidation state of manganese, which is ending up forming manganese dioxide, which is a brown color precipitate. So we saw that in the test tube B. And test tube D and E did not show reaction. Test tube D and E did not show reaction because the alkenes that we have here, which is ethene, does not react with ammoniacal silver nitrate or ammoniacal cuprous chloride. However, alkynes will react with both of these. Alkynes can react with ammoniacal silver nitrate or ammoniacal cuprous chloride to form metal acetylides. So, however, alkenes will not show this reaction. So, therefore, we do not observe any color change when you are reacting ethene gas with ammoniacal silver nitrate or when you are reacting ethene gas with ammoniacal cuprous chloride. With that summary, we can now move on to the second part of this experiment, where we will be producing an alkyne, which is ethyne or acetylene, and we are going to react the ethyne gas with these reagents and observe the changes that take place when we are reacting ethyne gas with these reagents. Now let's move on to the second part of our experiment. Now, in the second part of our experiment, we are going to observe how ethyne or acetylene reacts with different chemicals such as bromine water, acidified potassium permanganate, alkaline potassium permanganate, ammoniacal silver nitrate, and ammoniacal cuprous chloride. So, just like in the previous part of our experiment, we have bromine water here, potassium permanganate, we have Tollens reagent, cuprous chloride, and we have dilute ammonia, concentrated sodium hydroxide, sulfuric acid, distilled water. Apart from these reagents, we have calcium carbide, which is a gray color solid, right? So normally students, calcium carbide wouldn't have this gray color if it is pure calcium carbide. However, when you are producing calcium carbide or when we obtain calcium carbide in our labs, it could have this gray color. Otherwise, it is going to be colorless or white in color. Apart from that, we have our labeled test tubes. Just like in the previous part of our experiment, to each of these test tubes we will be taking different chemicals. And apart from our labeled test tubes, we have here a different setup. We have a conical flask here that is fixed with a rubber stopper, and to the rubber stopper we have attached a thistle funnel. Now, this thistle funnel is a good way to introduce small amounts of a solvent or a liquid into the reagents that we have inside our conical flask here. So, inside the conical flask, we are going to have our calcium carbide, and with the help of a thistle funnel, we are going to introduce water drop by drop or water little by little. This will allow the calcium carbide to come into contact with water in a well regulated manner, and it will allow calcium carbide and water to react with one another to produce acetylene gas or ethylene gas. These things do mean the same. Ethylene and acetylene are the same substance. Ethylene gas, or the name ethylene is our UPAC name, acetylene is our traditional name that we use, or common name that we use. So ethylene is a gas that is made up of 2 carbon atoms and 2 hydrogen atoms. So this is a alkyne. It has a carbon-carbon triple bond. So this ethylene gas that is produced can be taken out of this container with the help of a delivery tube. Now, another benefit to having a thistle funnel is when we are producing the gas that is produced will not be going out of the thistle funnel, because thistle funnel will be containing a liquid inside the thistle funnel. So the gas cannot climb through the thistle funnel and come out over here, and there is also a valve here that we can open and close to regulate the amount of water that we add to our reagents, or that we add to our calcium carbonate that we have here. So this is the setup that we will be using to produce ethylene gas or acetylene gas. Students, now all that is left for us to do is take these reagents into each of these test tubes. As we did in the previous experiment, we are going to first take into test tube A a small amount of bromine water. We have bromine here, or bromine water here. We are going to take our test tube A and add a small amount of bromine water. If the bromine water is too concentrated, you can further dilute it a little bit, because we have to take dilute solution of bromine water. As you can see, students, bromine water has this yellow color. This is a dilute sample of bromine water, or dilute solution of bromine water. So the color is not as dark as it usually is. However, you can observe a yellow color present here in our bromine water. And then to our test tube B, we are going to be adding alkaline dilute potassium permanganate solution. We are going to add alkaline dilute potassium permanganate solution. We have here a sample of alkaline potassium permanganate solution that we have prepared in the previous experiment, or in the previous part of this particular experiment. So what we have here is alkaline potassium permanganate that we have made with the addition of sodium hydroxide to potassium permanganate solution. Now, in this test tube B, we have dilute alkaline potassium permanganate. Students, the reaction with dilute potassium permanganate in alkaline medium with any unsaturated hydrocarbon is also referred to as the Bayer's test for unsaturation. Bayer's test for unsaturation. So this particular test will provide you a positive answer if the purple color seen here in alkaline potassium permanganate turns to a brown color, producing a brown color precipitate, which is MnO2. That is a positive answer for the Bayer's test, meaning when it comes to introducing any hydrocarbon to alkaline potassium permanganate, if the color of the alkaline potassium permanganate changes to brown, starting from purple, if it changes to a brown color, that indicates that the hydrocarbon that we have reacted with this alkaline potassium permanganate was unsaturated. So, Bayes test can be used to identify unsaturated hydrocarbons. As you know, alkenes and alkynes both are unsaturated hydrocarbons, so we can expect the ethane gas also to change the color of this alkaline potassium permanganate into a brown color. The reason for the brown color that you will observe is due to the formation of manganese dioxide, which is a water insoluble solid which is brown in color. However, this brown color solid is going to be produced as such fine particles. They will get dispersed in aqueous medium and will form a suspension. This suspension will make the aqueous medium appear brown. However, you have to make sure that you understand that it is not a solution that is formed when you form a brown color or when you observe a brown color in the test tube. It is not due to the formation of a solution. What you are going to be forming is a brown color suspension. So this is the positive result of the Bayes test. If you don't have an unsaturated hydrocarbon reacting with this alkaline potassium permanganate, there will be no color change. And to test tube C, we are going to be taking acidified potassium permanganate. So we have a sample of acidified potassium permanganate that we prepared in the previous part of this experiment. So we are going to be adding a small amount of acidified potassium permanganate into this test tube. And as you can see, acidified potassium permanganate is also purple in color. And as ethane gas reacts with acidified potassium permanganate, you have to observe whether there is a color change. And then to test tube D, we are going to be adding Tollens reagent, or in other words, ammoniacal silver nitrate. So we have ammoniacal silver nitrate. Let's add a small amount of ammoniacal silver nitrate into our test tube here. As you can see, ammoniacal silver nitrate is colorless. We usually use ammoniacal silver nitrate to identify the presence of aldehydes. What happens when we react ammoniacal silver nitrate with aldehyde and then heat up the mixture? We see the formation of a silver mirror. However, when it comes to alkynes, if the alkyne contains terminal hydrogens, these terminal hydrogens are going to react with certain cations such as silver plus ions or Cu1 plus ions and form metal acetylides. So these metal acetylides are going to be formed as precipitates. So in the presence of silver 1 plus ions here, when you are reacting ethane which contains terminal hydrogens, it will produce a white color precipitate, or it will produce a precipitate. When it comes to ammoniacal cuprous chloride, we have an ammoniacal cuprous chloride solution here. Now in the test tube E, we should have an ammoniacal cuprous chloride solution. Now students, even with an ammoniacal cuprous chloride solution, ethane can react to form a precipitate. It can form a metal acetylide with cuprous chloride as well. So with that in mind, now all that is left for us to do is actually produce ethane gas and then make ethane gas react with each of these reagents we have in front of us. So let's move on to that part of our experiment. Now students, as I mentioned earlier, we will be reacting calcium carbide with water. So when we are adding water to calcium carbide, we have to make sure that we regulate the amount of water that we add, so we can use the Thistle funnel to make sure that we add water to calcium carbide in a well regulated manner. So we have our conical flask here. We will open the flask, or we'll remove the stopper from the conical flask, and we can add a small amount of calcium carbide into the container here. So let's take a calcium carbide and let's add a small amount of calcium carbide into the conical flask. After we have added a small amount of calcium carbide into our conical flask here, we can go ahead and place our rubber stopper and seal the container with the use of a rubber stopper like so. When we are adding water to calcium carbide, we are going to be using the Thistle funnel we have here. So in the Thistle funnel, we have a small valve here. So when we add water here, we can open the valve and regulate the water flow into our calcium carbide. So to make sure that we do not mistakenly add a lot of water to the calcium carbide here, we will start with the valve closed first, and then afterwards we will open this valve and allow water to gradually fall onto our calcium carbide. So let's first of all close this valve, and we can take our water. We have distilled water here. Let's add a small volume of water into our Thistle funnel, and we can now proceed to open the valve and introduce water gradually onto our calcium carbide. You can see as soon as water came into contact with calcium carbide, there was a gas that is produced. The gas that is produced is going to be acetylene or ethane. So acetylene and ethane. Acetylene is a common name. Ethane is the IUPAC name that given to this hydrocarbon. So we will regulate the amount of water that is added, so that water is added drop by drop onto our calcium carbide that we have here, and we can move on to inserting this delivery tube into each of these reagents that we have here and observe the color change. Let's first take our bromine water and observe if there is a color change when acetylene gas comes into contact with bromine water. Ethane is an unsaturated hydrocarbon, and when we bubble ethane gas or acetylene gas through bromine water, you can very clearly see the bromine water is now getting decolorized. The bromine water is now getting decolorized. If you observe the color now, you can see bromine water is completely decolorized. Now let's move on to alkaline dilute potassium permanganate. In test tube B, we have alkaline dilute potassium permanganate. You can see when ethane gas comes into contact with alkaline dilute potassium permanganate, the color of the solution turns from a purple color to a green color first. This green color is there due to the formation of manganate ions. Potassium permanganate ions are purple in color. However, permanganate ions are green in color. That is why we see this green color that is formed here. And if you continuously bubble ethane gas through this solution, you are going to observe this green color manganate ion solution further reduces to form manganese dioxide, which is a brown color precipitate. As I mentioned in the beginning of this part of our experiment, manganese dioxide, which is formed, is going to be a water insoluble precipitate. However, due to dispersion of these fine solid particles, you are going to observe green color decreases gradually, and the color of the test tube or this particular suspension is now, and the color is now gradually changing to a brown color. So the green color solution gradually turns to a brown color. We can see that there's only little gas coming out. That is because water was not coming into contact with calcium carbide enough. Now we can see when more and more water reacts with calcium carbide, more and more ethane gas is produced, and when that gas is bubbled through our alkaline potassium permanganate solution, we can now very clearly observe that the purple color solution has now turned into a brown color. Purple color solution has now turned into a brown color. So let's observe what took place here. We started off with a purple color alkaline potassium permanganate solution, and when ethane gas came into contact with it, ethane gas got oxidized due to the presence of alkaline potassium permanganate and turned into oxalic acid. And it further can get oxidized into forming carbon dioxide. So while ethane gas is getting oxidized, we observed that when it comes to our permanganate ions got reduced. Permanganate ions are purple in color. When they get reduced, first, initially, they form the manganate ion, which is a green color ion. So the solution turned green. And upon further reduction, we form MnO2, which is a brown color precipitate. As you can see here, this is a suspension of MnO2 brown color precipitate suspended in aqueous medium here. So this is not a brown color solution, this is a brown color precipitate suspended in aqueous medium. Now let's move on to the test tube C. The test tube C contains acidified potassium permanganate. Let's observe what happens when we send ethane gas or acetylene gas through acidified potassium permanganate. Let's turn the valve and increase the amount of water that is flowing to the calcium carbide here, so we can produce more acetylene gas. And then let's insert this tube and observe what type of color change is going to be seen when we react calcium carbide and water and produce acetylene gas, and when the acetylene gas reacts with acidified potassium permanganate. What type of reaction takes place can be observed here. As you can see, little by little, the color of the acidified potassium permanganate is decreasing. Acidified potassium permanganate is turning colorless little by little. Now students, we can very clearly see the acidified potassium permanganate that we had initially had this purple color, but after we reacted it with ethane gas, the color that we observe here is colorless. This acidified potassium permanganate solution has turned colorless. This is because acidified potassium permanganate was able to oxidize the ethane gas, and as acidified potassium permanganate oxidizes the ethane gas to become oxalic acid and then later on further to carbon dioxide, the potassium permanganate got reduced. So as ethane got oxidized, potassium permanganate got reduced to Mn2+. So the Mn2+ aqueous ion solutions are slightly pink in color. However, it is going to be observed as a colorless solution. The aqueous Mn2+ ion solution is referred to as a pink color solution. However, in lab conditions, we are going to observe that as a colorless solution. So what you see here is the observation when you react ethane gas with acidified potassium permanganate. Now students, all of the calcium carbide that is in this container has reacted with water. So we are going to add more calcium carbide into this reaction mixture and then send the acetylene gas that is produced through our ammoniacal silver nitrate solution or the tolerance reagent and ammoniacal cuprous chloride solution to observe if there is any color change that is going to take place. So let's move on to adding some calcium carbide and continuing the reaction. Now students, we have taken a small amount of calcium carbide into our conical flask here. We are going to add water to it and produce acetylene gas or ethane gas. And we are going to send that produced ethane gas through ammoniacal silver nitrate, or in other words, tolerance reagent. So as you send acetylene through ammoniacal silver nitrate, you are going to observe the formation of a precipitate, which confirms the gas that is produced here is in fact acetylene. Acetylene or ethane contains terminal hydrogens, and these terminal alkynes containing terminal hydrogens are capable of reacting with solutions that contain Silver plus ions or even Cu1 plus ions and form precipitates. So let's move on to actually conducting this part of our experiment and observe the formation of a precipitate when we send ethane gas through our ammoniacal silver nitrate solution. So let's add a little bit of water to the acetylene, to the calcium carbide that we have here. And as acetylene gas is produced, let's introduce that into our ammoniacal silver nitrate. And you can see immediately as acetylene gas comes into contact with ammoniacal silver nitrate, a precipitate is starting to form. So this precipitate is formed because acetylene reacts with ammoniacal silver nitrates to form silver acetylide, which is a water insoluble precipitate. Now we can remove our delivery tube and observe the precipitate formed here. You can see that there is a precipitate in this test tube now. So this gray color precipitate that you observe, is silver acetylide. We will leave it aside for a while and observe it a bit more clearly after a few minutes. Now we will take another calcium carbide sample. We'll clean the delivery tube and we will insert it again into our ammoniacal cuprous chloride solution. Students, now we have cleaned the delivery tube and we are going to produce acetylene gas again and send this gas through ammoniacal cuprous chloride, which is our blue color solution that we have here in our test tube E. So let's allow some water to come into contact with calcium carbide and produce acetylene gas. And as acetylene gas gets produced, we will insert this delivery tube into our ammoniacal cuprous chloride solution we have here. And as you can see, when the gas comes into contact with the cuprous chloride, the color of the cuprous chloride begins to change little by little. The color of the cuprous chloride begins to change. This is due to formation of a reddish precipitate, copper 1 acetylide precipitate, which is somewhat of a reddish precipitate. We can see it is no longer blue in color. It is now somewhat reddish in color. Now students, you can see when we reacted ethine or acetylene gas with ammoniacal cuprous chloride, we can see the formation of a reddish precipitate. You can see it is getting coated on the walls of this test tube here, right? When I shake it, you can see there's a reddish precipitate that is getting coated on the test tube. Since the reddish precipitate is suspended over here quite densely, you might not be able to observe the color here, but over here you can very clearly see that we have formed a reddish precipitate, which is copper 1 acetylide. Copper 1 acetylide is a reddish precipitate that we can see that is getting formed. Copper 1 acetylide is a reddish precipitate that was observed when we reacted acetylene gas with ammoniacal cuprous chloride solution. Ammoniacal cuprous chloride was blue in color, but when we reacted acetylene gas with it, the product that was formed was a reddish precipitate, which is copper 1 acetylide. Now students, as a small additional part to our experiment, we are going to add water to calcium carbide and produce acetylene gas, and we are going to see how the acetylene gas burns in air. So as acetylene gas is produced and delivered through this delivery tube, we are going to burn the acetylene gas that is produced here, and we are going to observe how acetylene gas burns when we burn it in air. So let's first remove the stopper here and take our calcium carbide that we have here. We'll take a small amount of calcium carbide. And then we will place the stopper and make sure the valve on our thistle funnel is closed. After that, we can proceed to adding some water into the thistle funnel. And then we will proceed to slowly add water drop by drop onto our calcium carbide here. As calcium carbide reacts with water, it will produce acetylene gas. So we will now open the valve here and allow water to slowly come down the thistle funnel. As you can see, when water is added to calcium carbide, we can see acetylene gas is produced. And if you can take, after producing the acetylene gas, we are going to take the open end of the delivery tube and observe if we can light this open end of the delivery tube. You can see here, we are producing a small flame and the acetylene gas burns when we provide it enough heat. When it reacts with oxygen, it will burn, producing carbon dioxide and water. We'll observe it again. So can you see the acetylene gas burns here, producing a sooty flame, So this entire flame that we have here, so what you have produced here is a sooty flame, students. This is because the carbon to hydrogen ratio in acetylene produces a high percentage of carbon in acetylene. Therefore, when you are burning acetylene in air, due to incomplete combustion of this particular gas, there's going to be quite a bit of unburnt carbon, results in a sooty flame. That you observe here. Alright students, now you have observed the sooty flame that is produced from the acetylene gas. So now we can move on to the summary of this experiment. In this part of our experiment, we produced acetylene gas, or in other words, we produced ethylene gas. To produce ethylene gas, we reacted calcium carbide with water. As calcium carbide reacted with water, it produced ethylene gas along with calcium hydroxide. So the ethylene gas that was produced was taken out of a delivery tube and was reacted with different reagents that we had in these labeled test tubes. In the test tube labeled A, we had bromine water. And bromine water reacts with hydrocarbons that have an unsaturation. So as you know, alkynes are unsaturated hydrocarbons, which is due to the fact that alkynes have a triple bond in them. So ethine has a triple bond, so therefore it is capable of reacting with the bromine in bromine water. As the bromine molecules got used up when reacting with ethine, the color of the bromine water got decolorized. So you can see bromine water earlier was yellow in color, and after reacting with ethine, it is now colorless. So the bromine water got decolorized when reacting with ethane gas or when reacting with acetylene gas. Then we took alkaline potassium permanganate solution. When we reacted ethane gas with alkaline potassium permanganate solution, we saw the purple color of the alkaline potassium permanganate solution turned into a brown color precipitate. Actually, it is first, the purple color first changed to a green color, right? This is due to potassium permanganate, which is a purple color solution, forming a potassium manganate solution, which is a green color solution. And these manganate ions are going to get further reduced to form manganese dioxide, which is a brown color precipitate. You can observe here the brown color precipitate is now collected at the bottom of the test tube. We have left this precipitate to stand for a while. So as we formed it initially, it was observed as a suspension. But since it has been about 10 minutes from the time that we actually produced this manganese dioxide, we can see that the manganese dioxide precipitate is now collected at the bottom of the test tube. So when we are reacting ethane with alkaline potassium permanganate, ethane got oxidized, formed oxalic acid. It could further get oxidized to form carbon dioxide. And as ethane got oxidized, the alkaline potassium permanganate got reduced to form manganese dioxide, which is a brown color water insoluble precipitate. And then we moved on to acidified potassium permanganate. So when we are reacting ethane with acidified potassium permanganate, we can see the purple color of acidified potassium permanganate got decolorized, or the purple color disappeared and produced a colorless solution. This is due to the fact that potassium permanganate solution got reduced while oxidizing our ethane gas. Ethane gas got oxidized to oxalic acid, and sometimes it could further get oxidized to carbon dioxide, and potassium permanganate got reduced to Mn2+, which is observed as a colorless solution here. So the color change was purple to colorless. And then we took an ammoniacal silver nitrate solution and reacted it with acetylene gas or ethane gas. As you reacted this ethane gas with ammoniacal silver nitrate, we saw the formation of a grayish precipitate. This precipitate that is formed here is silver acetylide. When it comes to alkynes containing terminal hydrogens, they can react with heavy metals such as silver plus ions and copper 1 plus ions and form metal acetylides, which are water insoluble precipitates. So what you see here is a metal acetylide named silver acetylide, which is a water insoluble grayish precipitate. And when we reacted ethane gas, which is alkyne that is containing terminal hydrogen, with ammoniacal cuprous chloride, we can see the formation of copper 1 acetylide, which is a reddish precipitate. Again, students, we can see the formation of a precipitate here. What we have formed is a metal acetylide. I mentioned earlier a few seconds ago that alkynes that contain terminal hydrogens are capable of reacting with heavy metal ions such as silver 1 plus ions or copper 1 plus ions. So when it comes to ammoniacal cuprous chloride, it contains Cu1 plus ions, and this ethane gas that we send through this solution can react with the Cu1 plus ions to form copper 1 acetylide, which is a water insoluble reddish color precipitate. So the reddish color can be observed in the precipitate that is coated on the surface of the interior walls of our test tube here. So this brings us to an end in this experiment number 24. I hope you have observed how alkenes and alkynes react differently with different chemical reagents such as bromine water, acidified and alkaline potassium permanganate, and then we have ammoniacal silver nitrate and ammoniacal cuprous chloride. So we observed how ethene and ethine reacted with all 5 of these reagents. So with this information, now we can proceed to doing some additional questions and observing some more important theory parts revolving around this particular part of our practical in the next session. Let's move on to our questions now.